for anyone who hasn't been here yesterday. So my name is Sagi. I'm from Haifa University in Israel. I deal with mathematical evolution, computational evolution, and I build on the talk of yesterday. While yesterday it was quite slow and intuitive, today we will cover more deeper results, which as I expect from a research talk. So let's start. So evolution in the NGS area, new generation sequencing. The advent of NGS brought the hope of elucidating the history of life on Earth spanning 3.7 billion years and over millions of organisms. However, the abundance of genomic data revealed fundamental conflicts between various gene history, in the sense that we see that we analyze orthologous genes, okay, and different genes show different histories. These conflicts could not be explained as mere statistical noise, like we expect sometimes from different trees to be constructed. It was much more fundamental, the conflicts. Strong computational tools, along with a novel evolutionary paradigm, were required or have been required to explain and exploit these conflicting signals. And why to exploit, we will see during that talk. At the end of the talk, I start with with basics, very I think some deep theory, and I will get to that later. Okay. So what is a phylogeny? We saw that yesterday. This is it's a tree over a set of species, okay, a set of organisms that represents the evolutionary history of these organisms. Leaves represent our species set. The species set are located at the leaves, and internal nodes represent extinct species or speciation events, and branches represent evolutionary relationship. Okay, how is the talk outlined? I'll start with the basics of supertree. This is entirely not updated. Just a minute. Sorry. I am sorry for that. I am sorry for that. I will have to take it from my Dropbox then. Just a minute, okay? Sorry about that. Okay, so yesterday we started with and defined the. I don't like that as well. Just a minute again. I apologize for that. I practiced this. I modified it in another computer, and it was saved on the Dropbox. Anyway, here it is. So, talk outline. So yesterday we discussed the maximum quartet compatibility. We showed that quartets actually are the most basic units, are like the bits of phylogenetics, where if you any smaller unit than quartet, which is a triplet or unrooted triplet, is has no information or informationless. And so we saw that. So, and we show that when you get a bunch of such bits of information, you try to find some overall, some general history in the sense of a tree or in the form of a tree that explain most of them. And this task is called maximum quartet compatibility. We will show today the several dimensions of this problem, which is, like I told you and you could feel yesterday, that the talks are more in the context of combinatorics or basic algorithms. We will show that. This is quite standard in algorithms. And we start with existing results. We define a new and imperative variant called sample quartets. We will see how we break the third barrier, okay, the 1/3 barrier for sample quartet via the max cut approach that we saw yesterday, where the max cut approach started like a heuristic, which shows us some mode of operation or how some for students here, how tough research can go, okay? Then we move to the power of randomness, and we show a strong negative result. And we end with application to prokaryotic evolution. Okay, so this is the example we saw yesterday, okay, how we take several sources of conflicting or non-conflicting of history, evolutionary history, and we merge them into one unifying history. And now we again mention what are the quartets, and we remember that the quartet is the smallest informational unit, okay, where the only information is that that conveyed here is that 1 and 2, again, Farhad, 1 and 2 are clearly seen here because yesterday, okay, it's better than yesterday. Okay, so 1 and 2 are separated. That quartet tells us try to separate 1 and 2 from 3 and 4. Again, not any distance here. The 1 and 3 can be very near each other, while 2 and 3, their branches can be very far. It's only some combinatorial saying, okay, or restriction. Okay, so this is what it says. MQC, given a set of quartets, find maximum quartet compatibility, consistency, find as trees satisfying the maximum of them, or consistent with the maximum of these quartets, this input. Okay, quartet amalgamation stands at the heart of almost any phylogenetic task. And how we adapt, so yesterday we saw the max cut, okay, we saw the max cut idea, okay, idea or concept applied to triplets, to conflicting triplets, how we now, and you may remember that we had the bad edges between, in triplets, we had the bad edges between pair of neighboring species, and we had the good edges between any guy of the cherry to the out group. You remember that? Let's draw it here. Okay, so we have 1, 2, and 3 here. So we have that graph over 1, 2, and 3, and many more. But if you have 1, 2, and 3, we had the bad. No one has the red. The bad edge between 1 and 2, but we had the good edges here. So let's see how we adapt this idea into quartets. And we actually spoke about it. We showed it yesterday. We had the 2 bad edges here and the 4 good edges here, okay? And we also, and we assign weights 1, okay, positive unitary weight to the good edges and minus alpha to the bad edges. We will play with the alpha such that it will maximize. We will search the alpha that maximizes some objective function. Let's see. That computer, I saw that laptop actually doesn't show. The sigma on the computer I work at home is shown. Here it doesn't show. I didn't think about it. A maximum cut will strive to put cherries together, okay, to put this and this together, or to cut here, okay, and not anywhere else, to cut all the good edges. We note the multigraph, okay, so we here have these quartets. Let's see how this goes into the into our graph G of Q. So this is capital Q. So this is G of Q, and these, and here all the edges are from Q. 4 bad edges and should be 8 good edges here. I hope so. In G of Q, vertices can be connected by good and bad edges simultaneously. As you see, we just sum the weights of the quartet edges. Okay, so what are the dimensions of a problem? This is quite standard in optimization. So first, we have the density of the input. How much quartets do we see? So we start from just any size. It can be informational. It can be non-informational. We will see the concrete examples. I just marked here n square. Any idea what is the maximum we can have? What is all the quartets? So we just, if we have a quartet over a quartet tree over every 4 set, it is n choose 4, n choose 4, okay? So this is the maximum or the biggest input we can see. What is structure? So this is quite standard, or not standard, in any computer science or in any combinatorial optimization. What is structure? We will see soon, okay? So no structure at all, and here very structured input that we can, that allows us or provides us more information. What is the solution quality? So this is just the correct solution. And this is zero utility from the solution, okay? And actually we are speaking about approximation ratio, okay? So approximation ratio 1 is the correct solution. Approximation ratio 0 is when we cannot say anything, any guarantee to the solution. And eventually running time. So we are just, we say polynomial is any polynomial in all the parameters, and exponential is and regardless, of course, not regardless, but it should be polynomial or exponential in these guys, if at all. but nothing about that. Okay, and in particular, not the solution quality. Okay, so this is very standard. Okay, so what are the previous results? So first result from 92 was that actually the problem is hard, and this was quite a significant result because, come on, the triplet was so easy, and what's the difference? So this is the difference, that even when all quartets are consistent, as opposed to triplets where we had that divide and conquer, here not divide and conquer. Okay, so where that stands here in our problem dimension. So for any size, not any structure, we cannot assume any structure, and we will not find the exact solution in polynomial time. So we cannot expect for such a combination to exist. Okay, and actually by the type of the reduction yesterday was from feedback arc set with triplets, but inconsistent triplet. Here the quartets are consistent. The reduction was from betweenness. It's just a small detail. And because of betweenness, so we cannot even expect to have 1 minus epsilon approximation where we allow the time to be proportional to 1 over epsilon. So we will not even be here. Okay. So now, exact polynomial algorithms exist for special cases only. Well, if we have all the quartets, for example, and they agree, we have an algorithm. Even more general than that, if we have all the quartets for one guy, okay, one with all the other guys, or one with not all the other guys, but one or two, or any taxon appears in all quartets, we can root the quartets on this guy, and then have a triplet, okay, a maximum triplet instance, okay. So this is something. Now, something quite trivial we saw yesterday, the best approximation for the general case, again, any size, no structure, polynomial time is a third. We will have a third, okay, and naively by giving just random tree, any random tree, okay, even random caterpillar, okay, will give us a third approximation ratio, trivially. Okay, so and this is good, this is very fundamental, because whenever you get something which is worse than a third, just give me a random tree. Okay, so you don't want to see any time something worse than a third. Okay, and if your random tree satisfied less than a third, get another random tree. Okay, so very soon you will get a third. Okay, so the only until we started to work on it, the only rigorous result was something very, very restricted. You needed to have all quartets. They should have disagree. So all quartets, then you will, and so all quartets is very structured. Okay, you have a quartet over every, this is very structured. It's not only dense, it's also very structured. You will get 1 minus epsilon, and you will be running, it is called PTAS, okay, polynomial time approximation scheme, and you will run in time that is proportional to your epsilon. Tell me how accurate you want to be, how far from here, from 1, you will run proportional to that. Okay? So this is the, now, so that depends on epsilon, 1 over epsilon. So what is our first result? It's a seemingly very simple result. On the other hand, I like to speak about it because I think it is the last conceivable thing here, and yet very strong, simple and very strong and conceivable or understandable. So what we did actually is we observed the following thing. We improved to any. What do we mean by any? What we mean by any, as you see, this is like a log chart or a log scale, and any is like n choose 4 over 100, n choose 4 over 1 million, but any constant fraction or any constant fraction of n choose 4. So we know, and it can be just any structure. Of any structure, we know how to handle that. Let's see how we get that. Okay? So we do the following thing, which I like. So so suppose this is your input, this is n choose 4, and this is your input. We complement Q with all missing 4 sets, okay? All missing 4, every 4 set that is not in your input, we add it with random topology. Remember how many topologies? I mean, I adapt book down. How many topologies a quartet can have? Anyone remembers? From yesterday. This is one topology. 1, 2, 3, and 4. Anyone can think of any other topology? Okay. 1, 3, 2, and 4. Anyone can think about other topology? Still not? Okay, so the last, wow, okay. 1, 4, 3, and 2. So these are the 2 topologies. So I choose, and everything comes from here, guys. The third approximation, the random tree, everything comes from here. So I choose randomly between each such topology, okay, and I put it here, okay? I put it here. And now I simply run the pitas of these guys. Now the pitas of these guys is committed to return me 1 minus epsilon approximation, okay? So the return tree has no chance to satisfy anything better than assert here, and all the 1 minus epsilon, yeah.
Did the p-test require that all the quartets be consistent?
No. If they are consistent, then it's a special case that you have. For instance, 1 and all the guys, okay? So it will emit, when you have 1 and all the guys, you can just treat the quartet. You remove 1, and you have here 2 versus 3 and 4. Okay, so you can do that for all the guys. So when you have all the quartets, you can easily check if they are consistent, and if they are consistent, you take 1 out group and you do it like rooted triplets. Okay, so they by definition need to be inconsistent. Okay, so however here, we don't require anything. Consistent, inconsistent, we can, because this is already hard, okay, we just give a pitas. And we use their pitas. The thing is that we know that their tree will for sure satisfy only a third from all that new quartets that we added, and then all the approximation is applied to here. You need to adjust a little bit our epsilon, which is over the whole set, and their epsilon, but so it's something really nice, and this is sort of the last thing that I can expect to, not exactly, but I can expect people to understand, but let's see the rest. So what we did actually, yeah, why it doesn't show here? Anyway, okay, so yeah, so we have just any, we have almost all, which is somewhere here, not any structure, and we give the 1 minus epsilon. So let's see now the strong results of approximation. Okay, so to avoid constructing theta n to the 4 quartet, one may consider only a sample of the complete quartet set. So we sample quartet here. Okay, and that defines the sampled MQC problem. Quartets are sampled uniformly at random. So we just pick 4 guys, and we like an oracle. We have an oracle telling us what is their topology. Okay, so you pick 4 guys from the urn, I think it said, and you ask your oracle, hey, give me their topology. Okay, and the algorithm builds the quartet graph as we saw before, and applies the max cut on that graph, and the 0.425 approximation is obtained by providing a lower bound on the cut found and the number of satisfied quartets. We will see that more vividly soon. And this is the first time to break the third bound, okay, on not exactly structured input. Okay, so how we deal here? So we have the cut weights, okay, and recall our quartet graph. Every quartet contributes this, okay. So the 4 good edges of each contributes 1, and 2 bad edges minus alpha. Now a cut S in that graph, okay, we have a cut, partition the set Q of M quartets, so we have M such guys, and it partitioned this set, okay, into 4 parts with respect to S, okay, so we have the guys that are unaffected. So what is a cut? A cut is just we partition the species set, okay? So some quartets fall, all of them in one side. They are not affected by the cut S, okay? Some quartets are deferred, you remember, okay? So a quartet is deferred if the cut separates one of the guy versus the other 3. Okay, so this is, so this is unaffected quartet. This is a deferred quartet. Okay, so one is separated from the rest 3. This is a satisfied quartet. Okay, so 1 and 2 are separate in one side of the cut, and 3 and 4 on the other side. And violated quartet is here. And the weight of the cut S is as follows. Okay, so we have, so this is the set of, so this is a partition of our Q. Every quartet is either here, 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 and here. And these are the sizes of them, okay? These are the sizes of them. So we have these guys, the unaffected, they contribute 0 to the cut weight, okay? To the cut weight, they contribute, the cut to S, they contribute 0. The guys that are deferred, okay, deferred is here, they contribute exactly 2 minus alpha. two good edges are cut, minus alpha edge, okay? So the cut goes here, separates here. So one bad edge and two good edges. 2 minus alpha m sub d. 4, the guys that are satisfied, 1, 2, 3, and 4. And 2 minus 2 alpha is the guys that are violated. So this is the cut weight. Now I focus on a specific cut that surely exists in our Quartet graph. Okay? Listen. Every binary tree, this is very simple combinatorial fact, contains an edge that splits the tree into two subtrees, okay, where one contains beta leaves, the other contains 1 minus beta or n minus beta, okay, so and beta is at least a third. Think about it, okay? There is no tree that has no such an edge that separates less than third of the. You just need to go somewhere in the center, there will be such an edge, okay? So remember, our quartets come from some tree. They are consistent. They come from a tree. That tree must have that partition, that edge that separates to beta, 1 minus beta, okay? Now, so we know that beta is at least third. Now remember, we had that urn picking. So we know how our quartets distribute along that tree. And that cut exists also on our quartet graph, okay? So we denote that split by S sub 0, okay? S sub 0 is that cut in our quartet graph. And since we know that the quartets distribute uniformly over that species set, we can now know how many guys, or the expected number, okay, of quartets that fall 1 to here and 3 to here, or 1 to here and 3 for here, or any type of quartet. We know it from in our cut S0. The thing is to find it, okay? The thing is to find it. And as you remember, max cut is hard. Now, no quartet is violated. We have only these, the deferred, the satisfied, or the deferred, the violated, and the, the deferred, the satisfied. Sorry, I lost myself. Okay. Anyway, so we know how many, sure. Deferred, satisfied, unaffected. Unaffected for here, 0 here, or vice versa. Okay. So how they distribute? Beta to the 4, 1 minus beta to the 4 is the unaffected. You see that? All of the guys fall here, or all of the guys fall here. So this is the probability of that. And if we continue, so we have the expected number of quartets, the expected number of unaffected quartets, the expected number of deferred quartet, beta to the third 1 minus beta, or beta 1 minus beta to the 3, not to the third. Okay? And so also for these guys. So how exactly, so I jump. So I jump here. How exactly we get our approximation ratio? Very, very naively, but everything here is in the analysis. We get a bunch of quartet Q. We construct G of Q and alpha, you remember, alpha or 1 minus alpha, or minus alpha is the weight of the negative or the bad edges, okay? So we set alpha to 2, okay? So we have minus 2 for the bad edges. Okay, so here we have 1. This is minus 1 because we have minus 2 plus 1. Here we have 2. This is this edge, and minus 2. Now we run the max cut. Okay, so max cut, I told you, or I did not, there is an approximation, very classical approximation for max cut, Gomans and Williamson, that I did say it yesterday. It is based on semi-definite programming and something like similar to what we had, that mapping the points on the sphere, but this is n-dimensional, but it is polynomial, and it provides, it is polynomial, it is not randomized, and it runs in polynomial time, and it partitions the guys into x1 and x2. So we have that partition of the guys, and we have some approximation guarantee on that partition. Now the only thing we do is we construct random trees over these guys and these guys separately. So we get a third from these guys, and the profit that brought us over a third, okay, because here we have a third, is just the max cut here. So one may think why we did not continue recursively like in our max cut heuristic. It is quite involved, and it has to do with the randomness, that we lose the randomness here, but that brought us to here. Okay, so that's it. We join T1 and T2, and we return a single tree T max cut approximation. My computer is slow. My computer is slow. Just let's see. Okay, so we were here. So what is the contribution here? Just any size. You did not see any constraint on the size. Very, very structured input. We need to have every quartet with equal probability appearing. Okay, with equal probability. It is very structured input. This is the quality and polynomial time. Okay? However, randomness improves a lot. Apitas is the best that we can hope for MQC, because MQC is hard. We saw Pitas for any not sampled but dense input, almost all the quartets, like hundreds of all the quartets. Okay? We also saw that the 0.425 approximation for very sparse but sampled, very structured input. Can we hope for something in between? For instance, if we sample only n square log n quartets, somewhere in the middle, in the denseness, we have enough information to partition the taxa, the guys, into constantly many buckets, okay? Many, many buckets, but a constant, 100, million, but a constant. Now, we find the correct tree. We just search over all the trees. We find the correct tree over the buckets. There is only a constant number of them because we have million to whatever, or 2 to the million. It is still a constant. Everything is constant. It's not dependent on any parameter from the input. this tree satisfies as many as we want quartets, because the rest of the quartets in the buckets, we will have random trees. Okay, that brought us, so the input, so that we were here with our any size and uniform and the 0.425, and now we are here a little bit over n square, relatively sparse. Still, we needed the structure. We needed the randomness here. 1 minus epsilon. Okay, so we went all the way from here to here. 1 minus epsilon, but running time is proportional to 1 over epsilon. However, I want maybe to go now to some negative results, again obtained by probabilistic arguments. And it says something like that. So we see all the time that everything is based here on the structure of the randomness or subsets and all these. And the question is, how can we, if we have some structure in the input, and we check all, or even a random sample of subsets, or the subset of the given set, what we will be able to say on the compatibility. And this is the result. There exist sets Q of not very sparse n log n quartets. These are the size of the sets, such that every subset Q prime of Q, every subset of it, okay, of size a little bit smaller, okay, n over log n, is consistent, yet Q is very inconsistent. That means that that we cannot really hope for some sampling strategy over subsets, okay, that will tell us, that will give us indication. It is an area called property testing. Again, it's not me, but that says that no property testing here is an option. And let's see a little bit the idea behind here. So what we do is this. Just an overview, very schematic. We use probabilistic arguments to establish existence of the case. So if the probability of an event in a sample space, if the probability is positive, the event exists. We just kind of, turned around. So if we have something that occurs, okay, if we have like half of our guys are female and half are males, so in probability half we will find either guy. Okay, so we say if the probability is positive, the event exists. Okay? Now, we prove existence of two separate events by this approach. One is sets of the size that we want that are highly inconsistent. And one is sets of the same size of sets for which every subset of the assumed size, the subset, okay, n over log n, is inconsistent. So these sets and these sets need not be the same set. They are the same size, need not be the same set. If we have a probability of a third here and a probability of 1 over 100 here, they can be disjoint sets. However, if the sum of the respected probabilities, if we have here 2/3 and 2/3, there must be sets in the intersection such that they will be both inconsistent and every subset of them is inconsistent. So everything is probabilistic. It's not a constructive proof. Okay, so these are, we show that for random quartets, quartet sets of size n log n, O of n log n, with probability at least 2/3 there exist epsilon such that no tree satisfies. So this is very inconsistent, a fraction of that. Okay, so this is the 2/3 probability. Okay, so this is the number, so this is the size, all the sets of O over O of n log n quartet. This is all the sets, and we have here 2/3 of these guys satisfy this. No guy, no, okay, none of them have a tree that satisfies more than 1/3. On the other hand, we show that for random Q of size, same size, okay? So we deal with the same set of quartet sets with probability at least 2/3. We have that property, okay? Every set Q prime. So a point here is a set of n log n, okay? And for that point, every subset of O of n over log n is consistent. So all the guys here in the intersections are quartet sets of this size that satisfy both properties. Very inconsistent, and every subset is consistent. Now this paper is quite involved, and this is the most basic property of it. We had then extensions that to much denser sets, and there is a lot of play here with all the combinatorics and some, but this is some negative results of some direction that cannot be used, okay, that sampling subsets. Okay, it follows that the guys here satisfy both properties, okay, very inconsistent. There were related results, but they were not very inconsistent like ours, and so this is, now why all this is important? I have few minutes to speak. Why all these quartet games are important? So the horizontal gene transfer case, this is one case. The transfer of genetic material not through linear descent, a significant mechanism by which bacteria acquire antibiotic resistance. It is, so this is a big deal. HGT in medicine, in toxicity, in many medical antibiotic. Now it became antibiotic became big deal at NCBI. They started some initiative towards antibiotics, and you probably know more than I on this. So this is reflected by a horizontal edge connecting 3 vertical edges. Okay, so we have that. That is our species tree. How the species. However, this guy transferred some of its genes to this guy, and actually these genes, they exhibit a different history, and these are the conflicts that I spoke in the beginning of that talk. okay, the tree of life becomes a network of life, or this is actually, this famous figure is actually, I think, is denoted the spaghetti of life. And yeah, I don't remember from where I take it, maybe from for Doolittle, maybe from, yeah, I think this is for Doolittle. That is denoted, he's a big name in this. Now, so what can we do about HGT? So HGT is all over. HGT is all over. I think, Eliran, maybe you remember, but I think every gene is infected by HGT, including the most conserved genes like 16S that are the phylogenetic markers, like every gene. However, that doesn't mean that there is still not a vertical signal. And there is quite, I think it's quite accepted nowadays. Yeah, it is accepted that there is what is called the tree of life. Of course, Ford Doolittle would not agree on this, and he has some, but it is now quite clear to many evolutionary bacteriologists that there is a main trend of evolution that is called the tree of life, even in prokaryotes. Okay, so so why to look for that tree? And this is the positive results that we showed with Sebastian Roch that was here at that time, at 2012. We show that we can tolerate surprisingly large amount of HGT at every gene. Every gene can be very, very jumbled or infected with HGT, and still, if we look at the aggregate, we can distill, yeah, distill is the word, the signal, the tree signal, and obtain every quartet correctly. Okay, every quartet correctly. I think, Pavel, you asked why quartets. Here you see it. Okay, why quartets? You get big trees without this voting. Let's see how we do it. Okay, it's the idea. For every quartet, find the topology that is in majority in all gene trees. So we have 3 gene trees over 5 taxa, over 6 taxa, over 6 taxa. You see some, there was gene loss here. Here we don't see species number 0. Here we don't see 5. There was gene loss, gene transfer, all these things. And let's see what is the topology of a quartet. So let's focus on 1, 2, 3, and 4. And the topology, you see there the 3 topologies. So can you tell me what the topology in this tree over 1, 2, 3, and 4? Let me tell you the secret. This is 2 and 3 versus 1 and 4, thanks to this edge. That edge separates these guys. So we have 2, 3 versus 1 and 4. What is the topology over these guys, the same guys here? It is, again, 2, 3 are separated from 1 and 4. So we have the same topology. However, here it is 1 and 2 versus 3 and 4. Separated from 3 and 4, so separated by this path in the tree. But if we now do a voting, majority voting, we get that this topology wins, okay? And we have the theorem that if the number of HGT is very, very high, O of n over log n, then that topology is the correct one, okay? So all these gene trees were obtained by a series of heavy HGT on the species tree, the underlying species tree, but they were not more than this quantity, okay? N is the number of species. So we have some assumptions here, of course, again, uniformity of HGT along the tree, or a Poisson process that is uniformly distributed over the edges of the tree. And the corollary that the quartet tree can be constructed efficiently. Why? Because every quartet is correct. We can have them all. We simply have them all, okay? For every one of the n choose 4, we just do the majority voting, as Eliran does practically in practice. And we can now we get everyone correct, and we just run, not MQC, we just construct it because they are correct. Okay, negative results. Let me skip it. But this is, I mean, the negative result says that if we have a little bit more than that, n, but now times log n, then we will have some cases that we will not be able to see. We will get the same tree from two different trees, and we will not be able to distinguish. So I want to finish here. And concluding remarks, main issues, the max cut approach. So this is some lesson that I if I can, with my humble experience, I can tell that the max cut approach has proved guaranteed improvement. I started with the max cut by some game that as a student, and like I said yesterday, there was no chance of, because it was a heuristic that even the heuristic was NP hard, why to pursue it? And then then it appeared to be nice heuristic, yet it was not clear if this really provides any analytic advancement. And today we showed it does. The 0.425, okay, remained a big gap. So in our simulation, when we simulate the idea or simulate the input and we apply the heuristic, we get like as if we solve the problem, we just reconstruct the trees, and the rigorous analysis is, again, we have this only bad approximation ratio of 0.425, and that requires explanation. Why is that gap between the series, or between the performance? The power of randomness is instrumental in many settings here. Okay, so it gives a lot of structure. You saw it in the HGT just recently, two slides ago, and you saw it in the sample quartets. You saw it in the negative result. The randomness is a lot of structure. Simulations provide huge intuition. Again, if I can say, my humble contribution to students, and I remember when I started, it's a little bit of folklore, when I started my studies, and I approached my advisor from algorithms. It was not bioinformatics, and he laughed at simulation and coding and all these things. And now even he, not only that he moved to phylogenetics, even he does a lot of simulations, and his background is rigorous algorithms. Okay, open problems. I The third barrier for the general case is still open, and this is, I think few names are missing here, but it is, we had with Noga Alon from Tel Aviv University the negative results, and my students did not, are not entirely related to this, but that's it.